أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم بسم الله الرحمن الرحيم ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. We'll be continuing with the paper by Nicholas and O'Reilly, Learning Representations in a Gated Prefrontal Cortex Model of Dynamic Task Switching. So essentially looking at how the mind is able to switch tasks while also retaining information and understanding at the same time how these switches are comparable when it comes to weight-based memory mechanisms and working memory representation in the prefrontal cortex, and also looking at the other models in contrast to this. So we're gonna go straight into the previous portion, which is discussing the model. So it's important that I highlight first and foremost that unlike the typical Wisconsin card sorting task, the participants aren't simply looking at selecting the right shape, form, or number. They actually have to name the correct matching stimuli. So, the basic strategy to perform this task is a simple win state or lose shift type rule. If a positive feedback is received, continue the current subtask. If a negative feedback is received, switch to another subtask. Going back to the PowerPoint here, which was a summary, very briefly, looking at a few things. So, slide. Yeah, here we go, the model. So, a model of prefrontal cortex function that lends task appropriate context representations. So, task input here, stimulus goes into the hidden layer, which then relays back to the prefrontal cortex. It's a situation really where looking at analyzing at the prefrontal cortex not directly being involved but actually simply playing a part. So interesting thing I noted here was that the prefrontal cortex does not contribute directly to the input-output mapping task, but rather contributes by providing appropriate task-relevant biases. So it provides task-relevant biases. Okay. So stimulus encoding triggers activation of output units via hidden units. Hidden units are biased by reciprocal connections with PFC units, and PFC units are modulated by an adaptive AC unit. So the AC unit is ensuring that the PFC operates in the correct manner, right? So the task import is held constant, so it's not to be used. Why it's not to be used? I'm not sure. That's just how the model is designed at the moment. So the model, the simple layer represents the input stimuli using localist representations of features within dimensions. And so this sample layer represents the input stimuli using localist representation of features with dimensions, i.e., the first row of 3 units represents shape, second is color, so on and so forth. So each of these rows, as we see here, represents a dimension. So for instance, this row represents color, this represents shape, represents form, so on and so forth. Okay, so this is how each of these are forming. Okay, now this input is mapped via a hidden layer representing posterior cortex to an output layer, which represents the model's answer of a single active feature within one of the 5 dimensions. This input is mapped via a hidden layer representing posterior cortex to an output layer. Okay, input mapped by a hidden layer to an output layer, which represents the model's answer of a single active feature within one of 5 dimensions. Okay, the prefrontal cortex layer facilitates this dimension selection by providing top-down support or biasing. Now, I wanted to understand this a bit more in terms of top-down support or biasing. So, in a nutshell, you're looking at a scenario where you're actively looking for the object rather than the object presenting itself to you, right? It facilitates task switching by being able to rapidly update to another dimensional representation, thereby providing different biases. PFC, prefrontal cortex, does not contribute directly to the input-output mapping task, but rather contributes by providing appropriate task-relevant biases. The prefrontal cortex maintains an activation-based working memory representation for the current subtasks. To support this memory and to encourage coherent task representation instead of blends of different task representations, the prefrontal cortex has excitatory recurrent connections that enable units representing the same subtask to support each other. As described in the next section, the updating of this layer is influenced by the reward-based dynamic gating mechanism. So what's the gating mechanism? Quite frankly, I'm not entirely sure. As implemented in the adaptive critic AC layer, I'm just being real, which acts on excitatory intracellular currents within the PFC units. Aside from these key specializations, the prefrontal cortex units are otherwise the same as all the other units in the network. To enable exploration of explicit instruction in this task, we also included a task input layer where each unit represents a different subtask. During the naming task, as described previously, this task input is uniformly activated so as to not provide any discriminant information about the relevant task. So is this unidirectional? Yes. Ustaz ChatGPT here. Does this phrase mean it is unidirectional or a point here? You're a bit off point here. if you're reading that as unidirectional sentence, it's not about direction of processing. It's about whether the task input carries any useful signal to choose the task or right. So what it means is in the naming task, there is a task input unit group that could, in principle, tell the model which task it's doing. So task input, okay. So in principle, tell the model which task it's doing, okay. But they set it so it's uniformly activated, same level every time for all conditions. But they set it so it's uniformly activated. It's set so it's uniformly activated. So it gives no discriminating clue, no label like task A versus task B. No discriminating clue gives discriminating clue. Therefore, the model cannot use that task input to decide the relevant rule. It must rely on other mechanisms, maintained context in prefrontal cortex, gating, mappings. I was about to say mappings. So, therefore, the model cannot use that task input to decide the relevant rule. It must rely on other mechanisms. Right. Model cannot use that task input to decide. Model cannot use that task input to decide relevant rule. It must rely on other mechanisms. It must rely on other maintain context in PFC gating. It's like giving someone a hint card that always says the same thing no matter what the correct rule is. The card is present, but it's useless for distinguishing. Okay, so for example, having a ace of spades and you keep showing the ace of spades, right? And it doesn't distinguish from any others. So every time you pull out the card, it's the ace of spade, ace of spade. So they've kept the task input in the model here in a uniform manner. This one here. So that's quite interesting. Okay, so dynamic task switching model using so the prefrontal cortex extracts information from task that's inputted obviously, and the AC as I've tagged here, the adaptive critic AC layer, which acts on excitatory intracellular currents within the PFC unit. Aside from these key specializations, the PFC units are otherwise the same all other units. So where are we going? So this is a reward-based dynamic gating mechanism. So this is the reward. So it overlooks. So reward, as we know, is extremely important um, when it comes to the neuroscience, cognitive neuroscience of decision making. Okay, no problem. Right. So, okay, so if I just go back here, I have a few more questions. I It's not the task input is always extracted into PFC and agrees. It's the task input deliberately made useless, so it can't specify which context PFC should hold. Ah, okay. Right, so the task input, okay, is deliberately made useless, so it cannot specify which context PFC should hold. Is a clean way to think about it. What uniformly activated actually implies. If the task input is the same on every trial, then it provides zero information about which task rule is currently relevant. Okay, so I cannot push prefrontal cortex toward one context versus another. In other words, prefrontal cortex cannot rely on task input to decide the context. So I cannot push towards one. Okay, cannot push PFC towards one context. Oh, so PFC cannot and task input to decide the context. To decide context. So the model must keep the correct prefrontal cortex from elsewhere, mainly. So the model must get or keep the correct prefrontal cortex from elsewhere, mainly. Previously maintained context what it was already holding. Feedback reward driven gating, ACTD error, deciding when to update, and the model's learned internal dynamics, how it stabilizes one context state versus another. What happens in practice if the model is already holding the correct context? The uniform task input won't disrupt it. If the model is already holding the correct context, the uniform task input won't disrupt it because it doesn't favor alternative. Okay, the key is the fakir. If the model needs to switch context, the uniform task input won't help to choose a new one. The switch is driven by gating learning signal, not by task input. Mm, okay, learns from feedback and reward gating. Rather than task input. Okay, task input. Previously maintained context, but it was already. Hmm. So is it unidirectional? Not really. There is still a direction of influence of architecture. Inputs can be PFC. But here the particular input channel is non-diagnostic, so it doesn't create a clean, always agree pipeline. The important point is no discriminant information, no instruction. PFC context selection becomes internally controlled via gating plus reward history, not directly instructed by task input. Tiny example, imagine two tasks, name the color, name the shape. Task input is color or shape, it would clearly steer PFC. But if task input is always the same, like always task on, it's like saying you're doing a task. That doesn't tell you which one. So PFC has to infer maintain through other signals. Right, okay. How is such model created? Python, Windows, or what? Do you have any pictures that show how this model is developed in how is model workable for special laptops and CPUs, Caltech and MIT? Or see what it gives us. Stimulus usually. Very interesting. I'm just gonna do this. Complete section. Also briefly state the citations. Adaptive critic dynamic gating. Okay, so in this model, the PFC is like a mental notepad that was the current task rule, the current stimulus dimension to pay attention to. The big problem is should the notepad when the notepad when should that notepad be kept stable and when should it be wiped or updated? Section 3.1 so that users have to critic system to decide this based on prediction. Okay. Adaptive critic dynamic gating mechanism comprehensive. The adaptive gated adaptive critic AC gating. In this model, PFC is like a mental notepad that holds the current task group, current stimulus dimension to pay attention. The big problem is when should the notepad be kept stable and when should it be wiped or updated. Section 3 adaptive critic system to decide. Okay, PFC holds current task group, the current task group, the current task, the current, current stimulus dimension to pay attention to. The big problem is when should the notepad be kept stable? Problem should be kept stable. and should it be worked out dated utilization utilization of adaptive critic AC system to decide this based reward prediction uh, prediction. So the core idea is here. The model assumes working memory updating is driven by changes in prediction. Okay, okay, so start working updating is driven by changes in prediction. So if things are going as expected, that keep the current context. If things suddenly start working, change context. It's that easy. Okay. Okay, now it's simple. So if things go as expected, keep the current context. If things Start working. Change context. How the AC how AC does it? Temporal difference learning. So adaptive critic uses temporal difference reinforcement learning. Tries to predict future reward. Pause. Wasn't this done by excuse me, Aaron David Reddish? I think he's done this in mice. Work on mice. Aaron David future prediction. Right. So, so AC unit uses TD reinforcement learning. Reinforcement. Okay. Computes a prediction. Then computes a prediction error. Essentially, was the better or worse than expected. So what equation was used to calculate to implement TDR previous step? So now it's talking about dopamine production signals, midbrain, PA. PT. It's actually a fairly complicated paper. The unexpected reward predicting cue, dopamine burst. Expected reward missing. That makes sense. Unexpected reward and predicting cue, dopamine burst. Let's quickly read about what do you say? Ventral tegmental area, known as the VTA. It's simply a group of neurons located close to the midline on the floor of the mid. The VTA is the origin of the dopaminergic cell body, so mesocortical limbic dopamine system and dopamine pathways. It is widely implicated in drug and natural circuitry. This part here, with my book, Simon Weed, should be should be 'Got here finally, alhamdulillah. Right, so VTA, I remember I highlighted it specifically. Stuff from 25. Never mind. Anyway, dopamine burst, expected, missing, dopamine drop, i.e., reduced. What delta does to the prefrontal cortex gate? What delta does to the PFC context? So gate, basically. The adaptive critic delta signal, which is the reward signal, directly controls whether PFC context is stabilized or destabilized. When the network is performing correctly, the AC learns to expect reward that tends to keep the PFC context stable, so the model keeps applying the same task rule. When the task switches and performance suddenly becomes wrong, reward expectations are disconfirmed, so negative delta. This destabilizes the current PFC context, allowing the system to try different contexts to a different kind of rule. Interesting. This produces a natural behavior pattern. When stay loose shift. This produces a very natural behavior pattern. When stay loose shift. Keep the rule if rewarded, switch if not. The paper frames this as a kind of trial and error search over task contents. PFC contexts get activated and deactivated until one reliably predicts reward again. How maintenance is implemented in mechanistic detail. PFC is kept online using two things. Trial and error search. Go back to the basics for a second. Trial and error search. So here, going back to the basics on page 42. The distinction between productive and reproductive thinking has also been called a distinction between insight and trial and error. Meaningful apprehension relations versus senseless trial. Such context, PFC context, get activated, deactivated until PFC is kept online. Search connections. Okay. Acts stay delta control signal that control this. Okay, the network is performing correctly. Okay, network is performing the AC learns to expect reward, tends to keep PFC context stable, so the model keeps applying the same task group. AC learns expect to keep PFC context stable, so keeps applying, keeps hmm, interesting. Negative delta signals causes expectations to be discovered. Okay, stabilizes this destabilizes current PFC context. Destabilizes PFC text. System to try different. Our maintenance is implemented mechanistic PFC maintenance current M. Positive. Increase maintenance current for currently active PFC units persist. Negative delta decreases it. If delta is large enough, it can reset currents entirely strong, clear the null padding. Okay. keep it very brief. Okay, now computation of the computation of the reward. Hmm. So adaptive critic unit acts as the delta reward signal, which in turn allows us to understand based off the signal if the network is performing correct or incorrect. So our network depends on dopamine, is what this is being stated here. They're saying don't let one tiny mistake instantly trigger a task switch. So instead of sending raw, right, wrong straight to the adaptive critic, we smooth them. They average the last n steps, they use n, then they apply a threshold. If the average stays high, treat it as a positive reward, so mean is high. If if it drops below the threshold, treat it as a negative reward. Now it's really going wrong, so switching can happen. If it drops below the threshold, treat it as a negative reward. So essentially, you have a threshold, right? You have the ideal reward. I will do X, gain Y. It could be that your Y turns out to be a X. Pardon me, it turns out to be a Z, for instance. Yeah, something completely different. So in that scenario, you have to really understand what the systems where the system's gone wrong. Now, in this model, what they're saying is, look, one tiny mistake shouldn't make you just completely switch everything or switch the script. Instead, the average reward, where they averaged it using n as 2, if they then apply the threshold. So again, if average is high, positive reward. If it drops below the threshold, the average, the mean, then you have a negative reward. And once again, the average drops below threshold and triggers a real error signal. They reset the running average, so the new context isn't unfairly punished by errors from the old context. Right, so I want to unpack this more. So I really want to know this bit because we looked at the AC reward here, and the PFC, that's being the reward signals towards the context. The output is the final result. So yeah, just trying to essentially understand this bit. They're doing reward smoothing, a short moving average, so the model doesn't overreact to a single slip. But that creates a new problem, memory. The average remembers recent outcomes for a couple of steps. What goes wrong if you don't reset it? So imagine the model has just realized this rule isn't working and it switches context. If the reward average still contains all the bad outcomes from before the switch, then right after switching, the average is still low. If the reward average still contains all the bad outcomes from before the switch, then right after switching, the average is low. So that system is still looking like it's failing. Right, which would push the model to switch again, even immediately, even though it hasn't given the new context of a fair chance. So you get this messy behavior, rapid flip-flopping, panic switching. Okay, while resetting fixes it, When the average drops below the threshold, they treat that as a genuine something change on the okay. At the same time, they reset the running averages so that once a new context is tried, the reward signal going forward reflects performance under the new context, not the previous one. Tiny concrete example, suppose the average is over the last two rewards. You get two wrong trials in a row. Zero below real. Now you switch context. You don't need, if you don't reset, the context average for the next step is still dragging below these zeros. So even if the next trial is under the new context is correct, row 1, the average might still be low. So 0 plus 1 over 2. So you're still lagging behind despite fixing or switching, which can still look bad enough to keep triggering switching. Resetting after the switch, you start fresh and the new context is judged on its methods. Now, I forgot to look at this proposed dopamine. ربنا آتنا في الدنيا حسنة وفي الآخرة. Okay. When task changes, don't let the brain immediately fall back into. So inhibition, stopping prior task representations. So they added don't go back there mechanism. When the model is searching for a few new task the context is just use. Context it just use shouldn't be an option because they're almost guaranteed to be wrong after a switch. They say this is the inhibition of return. In visual search, once you've checked a place, your attention is briefly biased away from it so you explore elsewhere. Mechanism wise, they implement it as a negative bias weight. When a PFC context unit is deactivated, a negative bias quickly builds up. That makes it unlikely to reactive. That makes it unlikely to reactivate right away. Then the bias slowly decays back to zero, so the context becomes available again. The key claim is this acts as a very short-term memory of what was just active, and it helps stabilize task switching because it prevents immediate backtracking. So essentially, it's stopping the memory of a bad decision you made. So when it comes to task stabilization, which means positive dopamine rewards, because you got something right, they want to make sure there's no backtracking, so you're not catching up, as they stated in the simple example. You may get two trials wrong in a row, but moving forward, you might get a correct one, so 0 plus 1, and then 0 plus 2, and then plus 1, and plus 1, and plus 1. Averages make it seem like you are lagging behind. Right, so that is all for today. Inshallah, we will be looking at the rest of this as well. Inshallah, I'm going to finish this week. And from here, I'm going to move to Bisharo's model, look at the parameters and my critique of certain aspects and looking more deeply into the errors. So that's what these streams are all about, looking deeply into this. Assalamu alaikum wa rahmatullahi wa barakatuh.